Hi all, I am happy to present to you our work, which is a practical approach about measurement-based timing analysis on heterogeneous multiprocessors system on chip. This is done by Antoine Berthoud, Associate Professor in Computer Science at the University of Poitiers, Bernard Dautrevaux, Technical Director at AC6, Emmanuel Grolot, Professor at ANSMA and the Director of LIAS Laboratory, and myself, Roy Jamil, PhD student at ANSMA and embedded system researcher at AC6. In this presentation, we will talk about timing analysis in general, measurement methods used to get the worst case execution time, measurement results of our experiments, the AC6 tool system Workbench for Linux, heterogeneous multiprocessor system on chip, asymmetric multiprocessing measurement, and migration in heterogeneous architectures. Why timing analysis is very important. Several types of programs have to meet timing constraints, especially in the real-time systems domain, where critical tasks need to be executed before a maximum allowed time. In order to perform the timing analysis, we need to measure the worst-case execution time of some code on a given platform. This is important to get the safe upper bound of execution time. Several timing analysis methods exist. We can categorize it in two groups: static analysis or measurement-based analysis, like the dynamic analysis, hybrid measurement-based analysis, or stochastic timing analysis. Firstly, the static analysis based on calculating the upper bounds of the program fragments for a specific hardware. It needs a specific tool and faces a lot of problems, especially on modern platforms. The calculated worst-case execution time is very pessimistic. This is due to the uncertainty on processor's internal state because of caches, pipelines, memory access arbitration, using shared bus for multi-core, out-of-order execution, branch prediction, and so on. Another problem is that it requires a lot of work in order to add a new platform model, especially on modern heterogeneous MPSoC. On the other side, it is possible to measure the execution time on a running physical hardware or simulated. This measurement is based on physical timers peripherals, clocks, or using software APIs. The measured values are going to be used for the timing analysis. Several methods exist that are each featuring a unique selection of attributes, like difficulty, which is a subjective characteristic, where it depends also on the situation of the platform. Some methods are easy to access and to use, and others need special manipulation and setup in order to be used. The second is accuracy, which means how accurate or how close the measured value is to the true value. The accuracy is usually in order of a plus or minus a specific bound. The third is granularity, like measuring the execution time per function, process, thread, or it could be as small as an instruction. And the last, the resolution, which is basically the hardware limitation of the clock. It could be few nanoseconds, microseconds, or so on. So most of the measurement methods are based on a stopwatch technique, where the clock value is taken at the beginning, just before starting the measurement. Then, at the end of the measured block of code, the stop or the end value is taken. So the execution time is equal to the difference between the end and the beginning values. The measurement methods can be classed in two categories depending on whether an additional tracing probe is needed or not. In the case this probe is needed, the most popular method is using a logic analyzer. The main disadvantage, in addition to buying this expensive tool and installing tracing probe, would be the amount of time needed in order to retrieve the measurement data using this sophisticated method. But usually, this method gives a much accurate value with high resolution. On the other side, where no additional hardware tools are needed, the methods are classified in the case of an operating system like Linux is needed or not. In the bare metal case, where no operating system existing. The standard C functions like clock and time. So these functions are part of the C library used, which is available most of the time. The clock cycles counter, which is a counter attached to a core running at the same frequency as its main clock, and peripheral timer or counter inside the system on chip. For Linux or any Unix-based operating system, POSIX is adapted to be used in this case, using one of its clocks, like the clock real-time or clock monotonic. Here are some measurement experiments. We measured the execution time of the ADPCM_ENC or Adaptive Differential Pulse Code Modulation Benchmark, which is part of the TackleBench benchmark suite. This experiment was done on different boards like the NXP IMX7 ULP, the IMX8 MQ EVK, and the STM32MP1 DK2, which are all asymmetric boards. They have a Cortex-A and a Cortex-M. But in this example, we only use the Cortex-M4 running on bare metal. So the test was repeated for at least 100 times. We are showing the execution time as a box plot. You can see the maximum, minimum, median, and the values range. The results obtained using three measurement methods: the ARM cycle counter, the ARM core timer, which is the SysTick, and a peripheral timer, which is specific to each board. The results are similar across all three methods. This shows a consistency that is reassuring, since the only difference lies on the choice of the easiest method to implement. For Linux, we are showing the results of the same benchmark code, but this time using the POSIX clock on a Linux operating system in normal load condition or in a stressed environment using the Hackbench tool. We can see that the results in a stressed environment are more spread than in normal load. The execution time when measured in nanoseconds varies a lot depending on the frequency of the processor. Therefore, the IMX7, which has 500 MHz frequency, is the slowest, and the IMX8 running at 1 GHz is the fastest. So, if we calculate the equivalent cycles count, it gives closer value. We notice something that the execution time on the IMX8 board is faster on a stressed environment. So this is due to the fact that Linux changed the frequency dynamically depending on the processor's load. In this case, the frequency 1 GHz when normal load, while it's boosted 1.5 GHz in a stressed environment. System Workbench for Linux is a graphical IDE based on Eclipse and developed during my PhD at AC6. It aims to simplify the management of the embedded Linux platform, allowing non-specialists to manage their own Linux distribution. It can be combined with other microcontroller development tools. We developed the function measurement feature that injects the measurement code. It can be based on predefined method, or it is possible to implement a custom measurement mode. On the first figure, you can see the predefined measurement methods like the ARM DWT cycle counter. On the other figure, you can see the measurement code that will be used. Then, you specify the name of the function you want to measure and where it is defined, in addition to the different entry parameters value you want to pass. At the end, the tool will create a new Eclipse project with all the needed measurement code and options. This tool was used to measure the execution time of the experiment we have seen before. Heterogeneous asymmetric multicores are based on a system on chip that contains at least two different types of core, like for example a microcontroller and a set of microprocessors. This new technology is becoming very popular in the computing world. Popular heterogeneous MPSoCs families like the NXP IMX family, the IMX8 has a quad Cortex A53 with a Cortex M4, and the STM32MP1 family has a dual Cortex A7 with a Cortex M4. As you can see in this diagram, these different cores are connected at the same internal bus interconnect, and they both have access to the different shared peripherals and memory. Usually you can find a bus bridge, which is an intermediary connection between a bus and a peripheral running at different speed. In this example, we have, for example, a timer that will be used for the execution time measurement, in addition to the inter-processor communication controller, which is basically a signaling controller and a shared memory for communication and sending messages. This kind of architecture is very interesting because we can create application that starts on a core then migrates to another type of core. This migration is done through the inter-processor communication and the shared memory. So, how to measure the execution time of an application running on several clusters? The asymmetric multiprocessing communication is based on hardware intercommunication technologies like the shared memory, accessible by the different cores simultaneously, and synchronized using the signaling controller that triggers interrupts between asymmetric multiprocessing cores. On the software side, the AMP communication protocols are the remote proc that controls the lifecycle management of the different processors, start, stop, or restart remote cores, and the RP message, which is the messaging protocol. In this diagram, you can see that both the microcontroller and the microprocessor need these software protocol, and they can both access the shared memory and the signaling controller. To measure the execution time of a program that runs on AMP multi-cores, we should use techniques that are independent from any specific core. Furthermore, the cycle does not make sense as long as the cores are not synchronized and each has its own frequency. This is the reason why classical measurement methods are not valid, and we should use a time unit like the nanosecond or microseconds, where we take the same time reference. An on-chip external timer is a good choice in this case, as long as this peripheral could be controlled by all the AMP cores. It should be used like a stopwatch, where the start value is taken from the first core and then the end value from the last. In the example shown in the figure, we have two AMP cores. The start value is taken from the microcontroller and the end value from the processor. Our measurement method includes the execution time on both the microcontroller and the microprocessor part, writing the message to the shared memory in addition to the latency due to the inter-processor communication mechanism. The results shown in figure demonstrate the execution time in nanoseconds of this application, where benchmark parts were starting and ending on different cores. We can notice on all boards that sending a message from the microcontroller to the Linux operated microprocessor has higher latency but shows more determinism. The fact that there is more variation when Linux operates at the reader is due to the nature of the Linux scheduler. Most schedulers support migration only for symmetrical multiprocessing, but AMP migration could lead to a full resource mutualization. There is a lot of challenges in the AMP system because it has to deal with unrelated microprocessor platforms that use different instruction set architecture. The available solution is by simply compiling the code for each architecture and then specifying the migration point in the code. This will allow the migration from a cluster to another by transferring the values of the thread's local variables. The AMP measurement method presented before could be used in this case in order to measure the execution time of a task that migrates between AMP cores. To conclude, most clock-based measurement methods give similar results. The choice of the methods should rely on simplicity and accessibility. The AC6 tool System Workbench for Linux is an easy-to-use Linux build system and can be used to measure a function execution time. External clock or timer can be used to measure inter-cluster communication. AMP migration from a cluster to another is done using software preemption points. Thank you for your attention, and I'm now available to answer your questions.